We've established that the probability of an event E occurring is the size of the event space divided by the size of the sample space. We've done problems where we've created a tree diagram to see the entire sample space and then also be able to choose the elements of the sample space that make up the event space. However, that is very time consuming. And if we were to do an experiment such as drawing 2 cards from a standard deck, there's 1,326 different pairs of cards that you could possibly get. There's no way that you're going to create a tree diagram to represent this. So we need to now work on how can we get the size of the event space and or the size of the sample space in a much quicker way than creating a tree diagram. We need to develop counting techniques, otherwise known as combinatorics. To talk about counting techniques, we need to first establish 2 major questions that you need to ask yourself every time you go to do a counting problem. So let's read these 2 here. Problem 1. 7 people enter a race. The person who finishes first receives a gold medal, second gets silver, and the third person gets bronze. How many ways can the medals be awarded? And problem 2, 7 people wait for a cab. The driver says he only has room for 3. How many different groups of 3 could possibly ride? So I want to analyze these 2 questions. Are they the same or are they different? You may want to pause the video right now, think about that for a minute, and then resume. So to get an understanding of what's going on here, both of them have 7 people involved. Let's just call the 7 people A, B, C, D, E, F, and G. With problem 1, you could have for first place, B could finish first place, and say E could finish second place, and A could finish third place. That's one possible outcome, BEA. Down here in problem 2, again, there's also 7 people waiting, and 3 of them can ride in the cab. For example, you could have B, E, and A could ride together. That's one possibility. So BEA is a possibility up here, and BEA is a possibility down here as well. However, what about AEB? Is that the same outcome in problem 1? AEB is a different outcome than BEA. With AEB, A, let's say Adam came in first, Aaron came in second, and Beth came in third. So these are 2 totally different outcomes, this BEA and this AEB. Is the same true down here? If BEA went in the cab, is that different than AEB? Are those 2 different outcomes? No, it's still the same exact 3 people. The order of these people doesn't matter when they're riding in the taxi cab, whereas the order they finish up here is very important. So that's the key difference here. In the top one, the order matters, and in the bottom one, the order does not matter. So they are different. Even though they look fairly similar on the surface, they are significantly different. Let's look at 2 more. Let's revisit problem 2 again and compare it to a new problem. Again, problem 2 was 7 people wait for a cab. The driver says he only has room for 3. How many different groups of 3 could possibly ride? In this new problem, problem 3, there are 7 types of donuts at the coffee shop. If you want 3 donuts, how many choices do you have? Again, the question is, what's the difference between these 2 problems, or are they the same? You may want to pause the screencast here, think about this for a minute, and then resume. With problem 2, we established that if the people involved were named A, B, C, D, E, F, and G, that FAC is no different than CFA, for example, because 3 people riding in the cab together, the order of them does not matter. However, is there any sort of difference here? Hopefully you can see that the order would not matter here as well, because you're talking about 7 types of donuts and you need to get 3. But there's another big difference. For example, let's say A stands for an apple donut. Up here, Adam couldn't ride with Adam and Adam if that was one person. That doesn't make any sense. Whereas down here, you could get an apple donut, another apple donut, and a third apple donut, for example. Or you could get a B donut with an A donut and an A donut. So there's a big difference here. Up in problem 2, It didn't make any sense to be able to repeat any of the letters, whereas down here you certainly could when you're choosing three donuts out of 7. Nobody said that you can't get 3 of the same type. That's certainly possible. So the big difference between these two is up here at problem 2, you can't repeat, whereas in problem 3, you can repeat. These are the two major questions that you always need to ask yourself as you get into a counting problem. Here's a summary of what we learned in the previous 2 slides. The 2 key questions that you need to ask yourself whenever you're doing a counting technique problem: does the order matter, and can you repeat? Now it sounds simple, but sometimes it can be a little deceptive trying to figure out whether the order matters or not, and possibly whether you can repeat or not. So what we need to do is establish several techniques for counting that sometimes apply to when the order matters, other ones apply when the order does not matter, sometimes when you can repeat, and sometimes when you can't repeat. So we need to establish different counting techniques, and we have 4 total for this class. The 4 techniques are the fundamental counting principle, factorials, permutations, and combinations. The fundamental counting principle we've already looked at. We will quickly review that, and then we're going to establish these 3 new counting techniques. Recall with the fundamental counting principle that if task 1 can be done in m different ways, and another task can be done in n different ways, then the number of ways you can do them in sequence is m times n different ways. And this can also be generalized to any finitely many tasks. So we've done this, for example, if you have 3 sandwiches you can choose from and 5 appetizers you can choose from to make up a meal, then the total number of meals is 15. We've done this sort of thing already. However, we haven't explicitly stated this. Order matters in this scenario, and you can repeat. So we're now answering these 2 questions. So whenever you're doing a fundamental counting, using the fundamental counting principle, the order matters and you can repeat elements. The clear reason the order matters is because we're talking about an in sequence. In sequence implies order. You can repeat, for example, when we did the license plate problems, let's say you could put any of 26 letters in the first spot, any of the 26 letters in the next spot, so on and so forth. This allows us to repeat the letters here. So we can repeat when you're using the fundamental counting principle, and the order does matter. We now have a new counting technique known as factorials. So this n exclamation point, which is not how it's actually read, n exclamation point is read as n factorial. N factorial is the number of ways you can order n distinct objects. So if you have n different objects and you want to see the number of ways you can order them in a line, the answer would be n factorial. And the way you do that computation is you take n and multiply it by all the integers less than it down to 1. So for example, 5 factorial is equal to 5 times 4 times 3 times 2 all the way down to 1, which is 120. So what this tells you, if you had 5 distinct objects, there are 120 ways to order them. So very clearly, you're talking about the number of ways you can order them. The order matters with factorials. Also with factorials, you cannot repeat. So for example, if you had 5 distinct books that you wanted to order on your bookshelf, you'd have any of 5 choices for the first spot on the left. Then you do not then have 5 choices for the second spot because you've used one of them. There'd only be 4 potential choices for the next spot. And then only 3 for the next spot, and 2, and then finally 1 at the end. So you cannot repeat when you're doing a factorial computation. Notice this computation right here is using the fundamental counting principle. So problems where you're using factorials can also be solved using the fundamental counting principle.